you everybody for coming today. It's a great honor to speak, and this is a topic that is dear to my heart. I think is relative to this conference, combining both theory and practice. Let me start my screen sharing. Yeah, so as I mentioned, I'll talk about scalability. This is everybody's favorite topic. No matter what you're doing in the area of blockchain, then you care about scalability. And I'll try to say a little bit about what I've learned about this topic and where I think are interesting research opportunities and some of the lessons that I've learned. During this talk, feel free, if you have short questions, feel free to unmute and ask. And either I'll try to answer immediately, or I can tell you to delay that to the end. But feel free to kind of interrupt in the middle if you have a pressing question. Yeah. So what's the plan? So I first want to just talk about the next 10 years, and we'll try to envision how the next 10 years look like, and then we'll focus on this notion of Byzantine fault-tolerant state machine replication, which you all probably know. And what I would like to focus today about is kind of this difference between, I guess, the traditional view of what these systems do and what I will call this decentralized trust or blockchain systems do. And the main thing that will be different here is this additional ability of auditability. And I'll try to define what that means. And after we go to some notions and some definitions, we'll talk about how we scale these types of systems. And in particular, I'll try to divide and partition the scalability challenges into three parts, into kind of the liveness parts of these systems. Scaling liveness basically means getting more performance, right? So liveness essentially is a property of making progress in your system. If you can make more progress, if you can run more transactions, if you can have better latency and so on, that's kind of better liveness implies better performance. The other part is how do you scale the safety? And in that sense, scaling safety basically addresses the question of how you increase the security of your system. So we'll talk about providing systems that have better degrees of security. And finally, since one of the things that I'm introducing here is also this notion of auditability, I'd also like to discuss a little bit about why it's important to have auditable systems, and actually why scaling of the auditability of these systems is also important. After that, even though this talk is focused on kind of the state machine replication problems, I do want to talk about two more topics that are close to my heart, which are related to fairness and privacy. So depending on how much time we have, I'll say a few words about that as well. Okay, so as you probably are aware, we're living through a revolution, and this is kind of a digital revolution. And if you haven't been paying attention, this has been happening for at least a few decades. And the question really is, how will the next 10 years look like? And so I'll make a few very simple predictions that I'm sure you'll all agree with me. So first, I think is that we all agree that money is being disrupted, right? And we're seeing this kind of in this whole emergence of a cryptocurrency space, but even beyond that. And I guess my prediction is that money 10 years from now will be very different than what money is today. And so you can go and check 10 years from now and see if my prediction was correct or not. Next thing I'd like to kind of talk about is privacy. Privacy, I think, is one of the most important topics, societal topics of our time, and this is also being disrupted by technology. And again, I'd like to kind of say that I'm predicting that privacy will be very different than the privacy that we receive today. And I'm not making a prediction on to which direction this will happen. I do hope that privacy will kind of go in a direction that gives us a better trade-off between privacy and auditability, and we'll talk about that. But if I try to look back, let's say in the last 10 years, I'm not sure that I can say that society has made kind of a net positive progress on privacy. So there are some things that maybe are better and some things that are worse. But in any case, I believe that in 10 years, things will be very different. And more broadly, this whole notion of security and digital security is being disrupted. And again, I think in 10 years' time, it will be drastically different. And we're seeing this, more generally, that governance and politics and even how warfare is conducted is being completely disrupted by these revolutions. And I think the way I see this is that we as researchers have a burden and a responsibility to be a lighthouse and to explain the technology and to find ways to kind of provide positive progress in this area. So this was kind of a very short discussion about my future bets in the next 10 years, and I'd like to say, what is driving this disruption? And it's very clear, I guess, for all of you that modern cryptography is really a huge driver of this disruption. And at a very high level, this is kind of the topic of building protocols that replace trusted third parties. So this idea that you can kind of replace an ideal functionality with something that depends on kind of less ideal building blocks is essentially the core of what modern cryptography enables. And obviously, there's also a side of distributed computing and this decentralization and building these large-scale systems that can overcome network delays and tolerate failures. And what we're seeing is kind of the interdisciplinary research in between them is growing in importance. And we're also seeing that these two together are important, but there's also kind of a third very important force, which is the study of scarce resources and how we respond to incentives. And this is kind of the field of economics. And so, this is kind of my belief, and I've said this many times, that this multidisciplinary research is at the core of this new disruption that we're seeing. And indeed, the progress that we'll see in the next 10 years will likely come from interdisciplinary research in these three areas. And as this kind of technology becomes more important, we'll see that it drives disruption that is also related to things that are not traditionally hard science like math, but also related to political science, to law, to social norms, and how we as a society kind of govern ourselves. I think it's very important to understand how, I guess, this topic of governance interacts with all these things. So with that said, I'd like to kind of focus on today's talk about Byzantine fault-tolerant state-machine replication. And so, I'll say a few words about this. This is, in my view, I guess, this notion of state-machine replication is probably the most fundamental notion in distributed computing, and I guess you can view it as also a notion in cryptography. So really, it kind of starts by imagining this ideal world. And in this ideal world, you have clients and they want some service. And what we imagine ourselves doing is that we imagine that these clients are just interacting with some ideal, non-faulty centralized service, right? This is kind of this perfect world. And what we can do is mathematically formalize this ideal function or default functionality as a state machine. So that's why, I guess, in distributed computing, it's called a state machine replication. So this is a state machine part. We simply model this ideal functionality that we'd like to have as a state machine. And it's pretty easy to implement a state machine using one computer or one centralized system. And as you know, the problem is that ideal systems don't exist in the real world. Real world systems have failures and have malicious attacks. In particular, there's these two properties that typically don't hold: safety and liveness. So if you have a system that's centralized, then an adversary might compromise the system, and it can either break safety or liveness or both. So safety would basically mean that bad things happen, so there's some double spend, or liveness could happen, which is a denial of service or disruption or a censorship event. I'll also say that another problem here is that if you had some private state in your state machine, then again this state would not be private if an attacker compromised your system and can just read the internal data. So this is kind of the problem, and really state machine replication is the framework in which we think about these types of solutions, where we're basically saying, well, if one person cannot do it alone, then let's have a village and let's all work together to do something. And even if part of us are malicious or failed or compromised, then the majority will still prevail and will succeed in kind of getting a good outcome. And so this is this idea of using a multi-party state machine replication. Again, in the traditional literature, there's kind of two parameters, N and T, where N is kind of the number of servers. So this is kind of the replication factor. So previously we talked about using just one server, and now we're kind of talking about more than one server. So that's kind of the replication aspect. And this other parameter is T. And again, depending on the model, we're going to assume some threshold, and we're going to limit the power of the adversary to this threshold. So in particular, you can imagine saying that the adversary can control or compromise, no more than a third, or less than a half, or say everybody except one of the servers. And what you really want to do is you want to say, well, even under these very hard conditions, you maintain kind of safety, liveness, and even privacy, as long as kind of the adversary is limited under this model. And this is kind of the traditional approach in distributed computing. And one of the things that you can ask yourself, and definitely people ask, is, well, okay, you built such a system and it has such a very nice threshold. Maybe you can even prove that this threshold is the best you could hope for under some networking or modeling conditions. Then the question is, why would you assume that in the real world the adversary is bounded by this number, right? This is kind of a question that somebody from the outside would immediately ask, and sometimes we, as kind of people who write papers and work on these problems, don't kind of zoom out and ask ourselves this question. So I'm going to try to also ask that type of question, and maybe kind of relate that to this problem of auditability. So yeah, this idea of building state machines is not to build them kind of in an abstract theoretical model, but really to build them in such a way that they serve as a public good, or they serve a group of people. And in that sense, since this is something that's serving a group of people, then these people have a saying about the system. They can look at the system, audit it, and they can opine about the system. And so again, I'll just repeat the kind of traditional state machine replication approach. Byzantine fault-tolerant state machine replication has essentially two entities, clients and servers. And we're simply assuming that there's a limited size that the adversary can control of the servers, and then we kind of get these two properties, safety and liveness, that bad things do not happen and good things do happen, right? These are the two properties. And what I'd like to suggest kind of are these new systems. And the main distinction here, or the main additional functionality here, is that there's kind of another entity, which I'll call an auditor. But you can imagine these are the people that are using the system. If it's kind of the population, it's the population, or it could be a dedicated entity or a group of people, right, who's kind of dedicated to be auditors of the system. And I guess the difference here is that these auditors can now examine the servers. And by examining the servers, they can, in some extent, be able to punish misbehavior or reward good behavior. And this is kind of an additional safety layer on top of the assumption of a threshold adversary. So in a sense, we're saying, well, if a coalition of people manage to collude but are less than this kind of a threshold that the protocol allows us to tolerate, then the protocol will simply tolerate that. If the adversary somehow manages to accumulate more power than what this protocol enables, then what we hope is that there's going to be kind of an external system that will allow to audit and kind of be able to punish and reward this behavior. And again, the idea here is to try to limit the power of collusion in these cases. And again, the hope here is that under these assumptions, you'll still get these two properties of safety and liveness. And so when we talk about scalability, then typically in kind of the traditional systems, I'll say kind of on the left-hand side of this slide, what you try to do is you try to scale both safety and liveness. So scaling safety would be enabling higher degrees of security, and enabling liveness would would be enabling higher degrees of performance, right? So allowing more transactions to happen at once. And what I want to kind of focus today is saying, well, that's good and very important, and these are very hard and interesting research questions. But I also think that scaling the auditability is important as well. In particular, the ability of low resource entities to be able to audit and verify how these servers are behaving is an important feature of these systems. In a sense, this is kind of the way that we can check and provide balances against a set of servers that will collude above the threshold on which the protocol is kind of allows us to work on. So this is going to be kind of my main course for today. I'm going to talk about how to scale these three different aspects. So scaling the liveness, scaling safety, and scaling auditability. I'm going to stop here just to see if there's any quick questions or comments that people want to make. Okay, so what we'll do is we'll kind of jump into liveness, and this is kind of the thing that typically people, when they talk about performance, they say, well, I have some state machine replication system and I want to get better performance. So I'll talk about kind of this 4 bottlenecks, and I'll talk about, in my view, 3 interesting directions, research directions for how to scale. And this is kind of the vertical, horizontal, and hierarchical. Yeah, so this is kind of a schematic view of how these state machine replication systems work. And I guess my thesis here is that there are 4 stages that have to happen. And in a sense, your performance might be bottlenecked by each one of these 4. So, if you want to scale and get better performance, you need all 4 of these to kind of provide better performance. If either one of these 4 is bottlenecking, then it doesn't matter if the other 3 are, have a much higher performance, because many times, especially if you're talking about throughput measurements, then you're kind of bottlenecked by the lowest throughput. Similarly, if you're measuring latency, then again you're kind of limited by the part of the transaction that takes the longest time. So what are these pieces? So the first one is just the need to disseminate the requests from the clients to the servers, right? And this is kind of a very natural thing. But if you have a very large amount of data, or the requests that these clients are sending is very large, this actually becomes a bottleneck, right? And there are techniques, gossip techniques, and use of error correction codes and so on. And I think there's a lot of very interesting research in how to make sure that this part is not the bottleneck. After the requests arrive to the replicas, there's kind of something that we have to do, which is to reach consensus and decide what is the set, or the block of commands, or what is the next step of the state machine. And so inevitably we have to run a consensus protocol, and this is kind of where comes into play providing better consensus protocols. And I'll talk a little bit about that in a future slide. But what I want to say in this slide here is really that it's always this trade-off between latency and throughput. And I guess what we've typically seen is that you can always tune the latency and increase the latency such that the throughput will be large enough. So in many cases, what we've seen is that consensus is not the bottleneck. And really, what typically is the bottleneck is that the goal of this system is not to reach consensus on many things. The goal of the system is actually provide some public good, and this public good is typically executing some requests, right? So you have some business logic or something that you want to provide as a state machine that everybody sees. So actually, the value of the system is that it's executing these requests and reporting the outcome of the requests. And so typically, the part that is the one that has the highest requirements in terms of limiting the whole scalability of the system is execution. And really, this is just the part of once the commands are decided, you now have to run these commands on a deterministic state machine. Finally, after you've actually run these commands and you have an output, you need to persist this in some sort of persistent and sometimes authenticated storage. And here, again, we've also seen cases where actually the bottleneck is writing the outcome to a storage. And again, in particular, if this is kind of an authenticated storage. So for example, executing, say, EVM commands might be relatively fast, but then writing down the outcome to storage, in particular, persisting it on kind of a dynamic Patricia tree, is a relatively non-trivial task and might have a challenge in terms of kind of high performance.
Ittai, can I ask a question?
Yep.
When you say execution, as a bottleneck, you think of execution as a centralized operation or distributed operation?
Yeah, that's a great question. And I guess what I want to say is, I'll say a little bit more about this, but this is really, if you think about each replica, it reaches consensus, and then, it reaches consensus on a set of requests, and then it has to execute these requests. Say these requests are, payments. So you have to verify that the signatures are correct. You have to verify that the funds exist. So just that act of CPU time is expensive. If you're, say, paying an automated market maker, you have to kind of recompute the new value. So running these executions turns out to have non-trivial costs.
Thank you.
Yeah. So a few things about kind of performance measurements.
There was another short question.
Yeah, sure.
How does sharding fit into this picture?
Oh, don't worry. I have a whole slide on sharding. So
Very
yes.
good.
Yes. We're talking about scalability. So yeah. That's going to be the horizontal scaling. So I'm here. I'm just talking about one system, and soon enough I will talk about vertical scaling and horizontal scaling, and tell you more about that. So okay, so we're talking about a performance, and the naive way that I guess in the media people measure performance is by saying, okay, what's the transaction per second? And I guess as you all know, transaction per second is just a measure of throughput. And whenever you look at these systems, it's always a latency versus throughput trade-off. Right. This is kind of the fundamental thing that you trade between these things. And this goes back, maybe, David, to your question. The way I typically think about a throughput of a replicated system is by lower bounding it, by saying, suppose that we didn't have a replicated system. We really had just an ideal system, right? So what does this ideal system do? It doesn't have any consensus. Clients just send commands. It has to execute them. It has to persist them on its disk. So that would be the ideal throughput I would measure. Right. And I claim that, your replicated system can't do better than this ideal throughput, because at the minimum, you have to do that. So in many ways, the goal of a replicated system is to reach the same degree of throughput, or close to the throughput of an ideal system. And typically you do that through batching, right? This is kind of the main idea. You do less consensus with larger batches, and that gives you closer to the ideal throughput. The reason being is that you're spending less time reaching agreement and more time just running consensus, running the execution itself. And of course, this is at the cost of increasing latency. And so this is kind of I guess, a repeated lesson that we've seen in multiple systems, is that you can often get relatively close to this ideal throughput by kind of using batching, decreasing the amount of consensus, increasing latency. And that's kind of this throughput latency trade-off. This kind of a side note that many academic works that I've seen kind of look at this systems where the ideal throughput is essentially zero, right? So execution costs 0 time, and then like persisting is persisting something into memory. And typically what I've found is that these kind of workloads with no execution and no storage, they often distort the trade-offs, because they're kind of measuring a workload that sometimes doesn't match workloads that provide value, right? The whole goal of this of these systems is not to do lots of consensus. Nobody cares about that. People care actually about, again, as a public good, providing kind of a system where clients can interact and have business logic on the system, right? So what clients care about is actually the business logic or the public good that these systems are providing. And
so
I think, yep.
You mean ideal throughput is essentially infinity, right? I think.
Yeah, you're right. Yes, thank you. Yes. Yeah, yes. And yeah, and I guess I think there's kind of two interesting things here. So first of all, I think it's important to try to have some sort of standardized workload so that we can all measure systems relative to kind of standardized non-infinity instead of non-zero workloads that actually have some computational challenge and some storage challenge on them. And I do think, by the way, that it is a great research direction to look at systems where you actually care about ultra low latency, right? So sub-second, sub hundreds of millisecond latency is actually kind of a place where you can't play this game of, well, let's just increase throughput by increasing latency. So I think this is kind of an interesting research direction in that case. So this is kind of what I want to say about scaling about transactions per second. I'll say very, very little about consensus protocols. This is my favorite topic, but I kind of want today to talk about things beyond consensus. But I will say that there is kind of, I guess, all these modern state machine replication suggestions, and a lot of us here have written and suggested different variants. And to me, at least, I look at two canonical examples. I guess on the left-hand side is kind of Nakamoto consensus, and the right-hand side is PBFT. And really what we'd like to do is get kind of the best of both worlds. And so, I guess we'd like to have a minimized setup, and maybe proof of work has that, and some of these modern state machine systems don't. We'd like to have a very large amount of servers. That's kind of another thing that we'd like to do. We'd like to get the sub-second finality that PBFT does, say, unlike some of these proof of work systems. We'd like to get these very high throughput measurements, maybe 1,000 and even more. And in terms of kind of the total communication cost, we'd like to have these, this linear ability relative to, I guess, PBFT is quadratic. In terms of safety and liveness, again, you'd like to get even better properties than the current system. So in particular, for example, you want to have liveness even in asynchrony, and safety kind of in asynchrony as well. And obviously, people are interested in energy efficient consumption. So I'm not going to focus a lot about this part. I do think there are still interesting research directions in kind of getting the best of everything here, and trying to compare that to the kind of existing work, and also to kind of the two canonical lighthouse suggestions. So I promised you to talk about vertical scaling and horizontal scaling. So I'd like to say, here's one thing that we've seen is very helpful when the main bottleneck is execution, right? Where really you have a lot of transactions, and you want to somehow be able to increase the throughput of your system while keeping small latency. And so the high level idea here is you want to leverage the multi-coreness of modern servers, right? And be able to execute requests in parallel. That's very very common. If there's a problem, let's just throw more cores at it and get better performance. And ideally, you'd like kind of the execution to increase linearly as the number of cores increases, right? So double the number of cores, double the amount of performance. And there's a few challenges to this approach. So the first obvious challenge is that when you run requests in parallel, you get non-deterministic results. And this is really bad if you have a state machine replication system, because that means that different servers might not compute exactly the same order. And so some care needs to be taken in order to handle that. The second obvious problem is that, well, it's not clear that all transactions can happen in parallel. And this is really workload dependent, right? So if I'm just paying, then maybe paying is kind of commutative. It doesn't really matter if I'm paying David and Christian is paying Bas, or the payment is happening in the other order. First Christian pays Bas and then I pay David. So I guess, for some operations like payment, order is not that important, but for others, for example, if there's kind of an automated market maker, then the order really, really matters, because every transaction changes, I guess, the exchange ratio. So you have to be careful in kind of understanding what your workload is. And as you probably know, this is kind of a well-known solution, and this is what's called optimistic concurrency control. And the idea is that you can compute tentative outcomes without committing them. So you can say, well, given the current state, here's what I think should be the end state. And the advantage here is that this is where you get vertical scaling, right? You can now have 100 cores, and they can all run this thing in parallel. So this is really where you get all your efficiency. Obviously, then what you need to do is you need to, after you kind of decided the outcome, that's kind of the expensive part, you can commit to the ordering, that's the consensus part, and then you obviously have to resolve conflicts, right? So in the case that this ordering actually has some problems, then you need to decide on every request whether you accept the outcome that you optimistically computed, or you need to abort it and say rerun it again. And this is kind of, again, the thing that we're saving here is on the execution time. We're not saving on storage, because we're still doing the storage in kind of a critical section. And you've probably seen this on Hyperledger Fabric, and this is kind of this idea of executing and then doing the consensus, doing the ordering. And I guess, Hyperledger Fabric did this in kind of a non-BFT implementation, and all the transactions are optimistic. And I guess we're doing something similar in that sense. And we kind of add a Byzantine fault-tolerant solution to that. So we make sure that the pre-execution is safe and live. And we also allow for transactions that are both optimistic and pessimistic to kind of run in parallel. So if you have a type of workload where optimistic concurrency control fails, you can start it immediately in a pessimistic mode, or you can have a dynamic pluggable concurrency control system. So this is what I want to say about vertical scaling. I will say that this really allows you, if your bottleneck is execution, to get a very high degree of performance improvement. Obviously, the problem with this type of approach is that it could be that really what's limiting you is just your ability to write to disk. It's not your just ability to execute. For that, you can just add more cores, but there's kind of a limit to how fast you can write to disk. In particular, if you're writing to some authenticated data structure and so on, this might be a limit. And this is kind of where horizontal scaling comes into play. So somebody asked about sharding. So the idea here again is that you have some system, and what you're doing is you're going to partition this system into multiple systems, and in this way, each one of the separate shards can work in parallel, and you can spend execution time and storage time in each partition separately. And so this is very nice. And the idea is that you take the whole state and you kind of divide your state into each shard. And the hope really is that you get kind of a linear increase. So by kind of replicating the system, splitting the system into 3 different parts, you kind of get 3x more performance. Again, this is true if your bottleneck is kind of the execution and the storage. And obviously, this is not as easy as it sounds. So I'll mention 2 important challenges. So one challenge obviously is the fact that, well, this really works well if transactions only touch the data that is in one shard. But it could be that, if you sprayed your data randomly, for example, or if you have information that happens to occur in multiple shards, you might need to do some sort of cross-shard transaction. And I guess, there are solutions for this, again, kind of from the database community, 2-phase commit suggestions. There are also kind of techniques to reduce the frequency of these cross-shard transactions. And you can do this by kind of dynamically and finding smart ways to map the state to shards in such a way that most of the time your transactions will not go beyond the shard boundary. And again, I think there are interesting research questions about trying to optimize this and do this. I'll kind of mention another challenge here, which I think will emerge, is that there's kind of a non-trivial fairness problem. So, once you have these multiple shards, and maybe some assets are in one shard and some in the other, and that might give a fairness challenge where, if I'm on a shard with a specific asset, I might have an advantage over somebody who is kind of doesn't have his assets on that same shard. That's kind of one challenge, and the other kind of well-known challenge is, well, if you have just a set of n replicas and you just split your system into, let's say, 10 different shards, now you really want to hope that in each one of your smaller systems, you still kind of have an adversary that can control just a small threshold of your system, right? So if you took your system and sharded into 1,000 different shards, then really what you want to do is you want to hope that the adversary now, cannot control a third of each one of these 1/1000 system. And this is really a dream come true if you're an adaptive adversary, right? So if you're an adversary that can actually look at the way data is split and sharded, and then say, okay, now I'm going to choose how to, who to corrupt, then this is kind of really nice for you. And I do believe that people collude adaptively, right? Typically, people don't just collude out of random decision. So it kind of makes sense, oh, hey, we're all in the same shard. This shard is, maybe only 10 people, so maybe we can collude. And there are ways to overcome this. So I'll mention this idea of frequently reshuffling. Yes, we're kind of a shard of maybe 1,000 people, but after maybe 2 minutes, we get reshuffled into a different shard. So by the time we try to collude, it's already too late. And so this is indeed very nice, and this can even formally help against adaptive adversaries. Obviously, this adds new problems, right? If we have to maintain this shard, then, well, we have to get all the history and all the data that happened before us. And so now this is kind of a hard problem of transferring the whole state. And again, there are kind of interesting techniques. I'll mention kind of stateless validation techniques that might help you remove the problem of transferring state. So this is what I wanted to say about sharding and horizontal scaling. But since there was a question earlier, I want to see if people have more questions or comments. Good. So yeah, I'll quickly go over kind of horizontal scaling because I see we're running out of time. And yeah, so I guess in kind of horizontal scaling, the high level idea is that we're going to use the layer 1 system and then kind of execute our transactions on layer 2. And then we're allowed to go back to layer 2. Again, we kind of scale linearly. And I guess, there's kind of two challenges. So one challenge is that this data that happened in layer 2 will go away. And there are ways to kind of solve this. One of them is basically to record the data on kind of a side chain. Another is to record the data on L1 itself. That's kind of the rollup solution. And again, there's kind of problems with a malicious operation. And for that, we're kind of use fraud proofs and succinct proofs of knowledge in order to kind of prove that this operation went well. So yeah, I'm going to quickly, I guess, glance over safety because I want to kind of touch on auditability, and really kind of say that some of the goal here is to kind of get better auditing. And so just like kind of this L2 or roll-up solutions, the approach was that it is audited by L1. I guess what I want to kind of convey is this idea that these L1 systems are essentially audited by the people, by the people who are running or using the system. And here I kind of just use L0 as a name for kind of the people themselves. And really, what is the role? So the role of us, right, or the people who are kind of auditing, is to punish and reward L1 for their behavior. This is done economically by having a market for tokens that represent the different L1 systems. This can happen legally by having nations and jurisdictions impose laws and regulations. And you can choose which fork to win. And I guess my hypothesis here is that systems that have better auditability and have more scalable auditability will prevail. And here really is the problem is without auditability, somebody can say I have this amazing BFT, but it's just kind of a theater that we're all enjoying watching. It's not clear that the system is actually doing anything meaningful. And so I guess kind of the non-scalable auditing is a traditional approach where the auditor just kind of runs the same executions as the replica. And we know it's expensive, so we have to find a way to kind of reward the auditor appropriately. And we also want to make sure that the auditor itself is not malicious, so we want to use cryptographic techniques, and we want to be able to punish malicious auditors. And kind of this doing a scalable auditing system is actually hard, and this is hard even in the real world. This is kind of an example of the American tax system, which essentially tries to audit U.S. citizens and is struggling with basically not being able to scale well. So here's kind of a quick sketch of the challenges of auditing a state machine system. So for data, you want to make sure that the client requests are treated fairly and not censored. You want to make sure that consensus actually works. You want to make sure that execution is done correctly, and finally, you want to make sure that that the data is really available. And auditing kind of client requests. That's making sure that clients aren't censored by the primary. And I kind of I'll mention this idea of rotating leaders, and PBFT has an approach, and also this very nice recent paper in OSDI 2020. And consensus auditing is also another challenge, and there are kind of interesting things about that. I'll skip that today, and I'll talk about kind of auditing execution. So there's this idea of an optimistic roll-up where basically people can commit to what the next stage is, and other people can then kind of provide a proof saying no, this person committed fraud and did not kind of provide the right state of change. And both of these are done by issuing some bond. So you have some economic risk related to this claim. And there's kind of an on-chain protocol that allows misbehavior to be kind of punished and correct auditing to be rewarded by kind of slashing the bonds and so on. So this is kind of this idea of auditing. There's kind of obviously an even more stronger solution of kind of verifying execution. And this is kind of the magic of succinct arguments of knowledge. Again, this is this amazing ability that you can verify work much more efficient than actually doing the work, right? And this again is kind of a way where you can scale the power of an auditor. Finally, I'll just talk very quickly about two problems in terms of state. So one of them is related to authenticating the state itself. So if you have a large amount of state, how can you prove a small piece of this state is correct? And this is kind of this topic of authenticated data structures. Again, there's a lot of really interesting research around that. And there's kind of this problem of data availability. Again, I'll kind of glance on it, but really the problem here is, how do I verify that the servers that are providing this solution are actually storing the data and making it available for other people to read, and not just censoring the data and hiding it. So that was kind of I guess a quick overview of kind of the three different aspects of scaling decentralized trust. I guess I plan to talk about privacy and fairness, but I'll skip that. So I'll just kind of conclude here with questions. And just summarize. So we talked about kind of Byzantine fault-tolerant state machine replication. I kind of added this new notion of auditability, and we talked a little bit about these three dimensions of scaling these systems: scaling liveness, so providing better performance; scaling safety, which is improving the security of the system; and finally scaling auditability, which is to basically reduce the burden of auditors, so that weaker and lower powered auditors can basically efficiently audit a high performance system. Right, and with that, I thank you for your time, and if there's any time for questions, I'll be happy to take them.